Hello everyone, I'm Panos, and on my free time I'm developing AnKi 3D engine. In this presentation I'll be going through the GPU-driven implementation in AnKi, but before we start, a disclaimer. What you're about to hear and see does not represent the views of my current or future employers. This is going to be the agenda for this presentation. We'll give an intro to GPU-driven rendering, or at least we'll try to. And then we'll dive into the implementation step by step. First, we'll discuss the GPU persistent data, then we'll move to GPU occlusion, then Meshlet rendering, mesh shaders as well, and finally some performance numbers. Right, so what is GPU-driven rendering? If we can say it in one sentence, maybe we can say something like GPU-driven rendering is a set of techniques and technologies that aim to migrate work that is associated with rendering from the CPU to the GPU. And we have some examples. Maybe we can categorize it as GPU-driven, maybe not, but the most rudimentary use of it is in GPU simulations, things like particles, skinning, water simulation, object placement, etc. Things that engines used to do in the CPU a decade or so ago. The next real use of GDR is GPU occlusion culling. This can be done entirely or partially in the GPU. Last stop is generated commands from the GPU itself. Here we have the X12's extended indirect and its ultcan counterpart, which is now KHR device generated commands. This is a newly released extension. And a more recent addition is workgraphs. Right, what GDR is and isn't. First, we need to establish that because GDR is a chaotic topic. It has many variants and comes in many shapes and forms. It is a collection of technologies pieced together. This can be API features and rendering techniques used together in unique ways. GDR doesn't require special API functionality or very recent GPUs, because rudimentary GDR variants are possible if the API and hardware support something like compute shaders and indirect commands. Another point is that GDR enables new possibilities, and for that reason sometimes it includes adjacent technologies that interact with it but not necessarily conform with its primary directive. Some examples are visibility buffers and mesh shaders, which are orthogonal to GDR, but on the other hand, they work quite well with it. Another interesting aspect of GDR is that it shares some similarities with ray tracing. For both GDR and ray tracing need almost identical ways to access data. Unfortunately, this is where the similarities end. The geometry part of ray tracing and raster are often two different things, so there are more bridges that we need to build in the future. But why care about GDR? The first reason is that year-over-year growth of performance is higher on GPUs than CPUs, at the present time at least. So what naturally happens is more workloads migrating to the processing unit with the highest performance, which is often the GPU. The second reason is games consoles. Consoles often drive AAA gaming, and they are often the mid-spec and the target platform. Current and previous generation console architectures paired underpowered CPUs with fast GPUs. This CPU-GPU dynamic led to game engine developers migrating lots of work to the faster GPUs. The third reason is that GPUs are quite capable of processing lots of similar data in parallel. games become bigger and the amount of data that it needs to get processed also increases. We have more objects in the screen, more particles, more skin characters, etc. More data processing is apparently a natural fit for GPUs. Last reason is that often GPUs contain data that we can use for various operations. The best example is the depth buffer, that it can be used for occlusion culling. So instead of transferring it to the CPU, so we can do the occlusion culling in the CPU, might be wasteful. So we can keep it in the GPU and do the culling there. So now let's focus on AnKi. The work I am going to describe was split in 3 parts. It would have been a monumental task and a huge risk to do everything at once, so the work was split. The first part is persistent data, also known as GPU scene. The second part is GPU occlusion culling, and the third part is extending this GPU occlusion culling by making it more fine-grained. And here are a few more details about the 3 parts. GPU scene mirrored part of the scene graph to GPU's VRAM. Things like objects themselves, object transforms, uniforms, material properties, etc. Textures become always available to the GPU as well, which means bindless, at least in our case. Buffers were consolidated into a few larger buffers. Draw call building became faster by eliminating pre-draw call resource setup, like uniform uploads, descriptor sets updates, etc. Vertex shading also changed with the use of programmable vertex pooling. And finally, the GPU scene unified the resource accesses of both ray tracing and raster paths. So both paths now use the same ways to access textures, vertex data, uniforms, etc. The second part is implementing the GPU culling. So all culling happens now in the GPU, and that includes frustum culling. Visible objects are drawn in batches grouped per graphics state. CPU times improved quite a bit in this step. The final step was to extend the culling to submeshes, also known as meshlets. This part enabled the use of mesh shaders and pushed the geometry throughput even further. Let's move to the first part. Now let's compare what happens on the CPU side with the GPU scene versus a more traditional renderer. So on the left, the more traditional renderer, it has visibility spread across multiple CPU threads. There is also visible object sorting. Then for every visible object, we do the following. We update the uniforms, also known as constants. Maybe create a descriptor set and populate it with textures, samplers, buffers, etc. We bind that descriptor set. We also bind the vertex and index buffers. And finally, we bind the BSO. Maybe sometimes we bind it, maybe sometimes we don't, depends. And finally, we have our draw call. Now on the left, we have the new way with the GPU scene. It starts the same with the visibility and sorting in the CPU, same as before. But what changes is inside the render pass. So now, for every render pass, we bind the bindless descriptor set once for all draw calls. We bind another global descriptor set once for all draw calls. Same thing for a global index buffer. And then for every draw, we just maybe bind a BSO and draw. The CPU work that is happening per draw with the GPU scene is less. Setting up resources is done at the beginning of the render pass and for all draw calls, unlike the old way. Data are organized into three global data blobs. The first is the GPU scene itself. This one contains a GPU view of the scene graph, as we mentioned before. And this is a collection of arrays, one array per GPU scene data type. The second blob is the unified geometry buffer. This is a large buffer that contains all index and vertex buffers of all the meshes loaded in our scene. All geometry data are actually suballocated from this big global buffer. The third blob is the bindless textures. This one contains all the textures referenced by the objects in our scene graph. In Vulkan, we use the KHR descriptor indexing extension, and it's a single descriptor set that contains practically all textures. In DX12, bindless textures live in the first part of the global CBV, SRV, UAV heap and accessed using shader model 6.6. Now, the GPU scene has multiple data types. We have, for example, the renderables, particle emitters, lights, reflection probes, indirect diffuse probes, decals, fog density volumes. We have the transforms, and we also have bond transforms. And then on the left, we can see some special structures. We have the renderable bounding volumes, which is more or less an ABB of the drawable scene graph objects. We have one array per rendering technique / pass. We'll see later what exactly that means. Then we have uniforms, also known as constants, that an object requires. These are suballocated out from this GPU scene buffer, and they're not in an array like the others. Uniforms contain the indices to the bindless textures and in general material properties an object requires, like a color or similar stuff. Here we can see the relationships of the drawable scene graph nodes. Let's start with a transparent object. Here we look at the transparent renderable bounding volumes array. We have one element here, and that points to the renderables array. Here we have all the renderables, and the renderable points to other stuff, like a particle emitter structure in this case, and also to the uniforms. So yeah, the green part is a particle emitter. Now the orange is an opaque object. Think of it as a column in Sponza, for example. Here, this one is rendered in the gbuffer pass, so it lives in a different array of renderable bounding volumes. It points to the renderable, and the renderable points to uniforms, transforms, bond transforms maybe, and the Meshlet, which are practically descriptors of the geometry. The renderable points to two transforms, one for the current frame and one for the previous frame, and that is to calculate the motion vectors. And it also points to up to 3 Meshlets, one for each level of detail. The Meshlet point to the large unified geometry buffer that we mentioned before. Here we can see some actual structures. These are shared between C++ and HLSL. We start with a renderable bounding volume here, which packs an ABB and also a sphere radius. We'll see later why. It also points to the renderable here. This is very small and thin data structure, just 32 bytes. And it needs to be small and efficient as possible because GPU visibility testing, which we'll discuss later, will actually hammer it. The renderable is here, and it's primarily, as we mentioned, a collection of pointers. It points, for example, to transforms, it points to constants, it points to the Meshlet, which is this structure. Maybe it points to bone transforms, maybe to a particle emitter structure, and it has a few additional things. Non-particle emitters, as we mentioned, point to this Meshlet structure and contains pointers to the vertex streams, the index count, if it's an index draw call, the first index, and also here you can see some data that are used to decompress vertex data because some of them, like the position, are quantized. And it also points to it also have the bindless address, bottom level acceleration structure, because we also build the TLAS in a GPU-driven manner. One last thing to mention is how we update the GPU scene from the CPU. The whole process is called micropatching. The game logic gathers patching requests in some CPU visible staging buffer. For example, if an object has moved, its transform will need to update it in the GPU scene. So this object creates a micropatch request. Then the renderer gathers all micropatches and dispatches a single compute job to perform the update. Patching doesn't show up in profiling, and we haven't spent much time optimizing it, and that's why I will not go into details on how it's actually implemented. Final stop is the unified geometry buffer. As we briefly mentioned before, UGB is a single large global buffer that is visible by all subsystems. All vertex and index buffers are suballocated from UGB. Vertex data are exposed in shaders as text buffers, also known as type buffers in TX. Most objects have like 3 vertex attributes, which are the position, normals, and UVs. Tangent is reconstructed in the fragment shader. Here we can see some examples. We have a UGB bound multiple times depending on the format that we care. So for example here we bind the UGB as an RGBA 16U norm texture. This is for positions. And then we bind the UGB again as a different format, RGBA 8S norm for normals. Similar story for the UVs. One small note is that positions are stored as signed normalized values of 16-bit, and they are scaled and transformed in the vertex shader. This is done to save on bandwidth. Now let's talk about GPU occlusion culling. And more specifically, we'll be talking about how we do all the visibility testing in the GPU and how we draw the surviving visible objects using multi-draw indirect. Multi-draw indirect is a term borrowed by OpenGL. But before we start, let's define the render state bucket because it's a concept that we'll be mentioning a lot. Renderable objects can be drawn using various rendering techniques. A tree in our scene, for example, may be drawn in the gbuffer pass and in the shadow passes. So this tree belongs into 2 passes. At the moment, the engine supports 3 rendering passes for rasterization, which is gbuffer, shadows, and transparents, and 2 for ray tracing, ray trace shadows and a general zip buffer like thingy that is used for reflections and it will be used for GI in the future. Every pass has a collection of render state packets. The render state packet essentially defines the graphics state that the renderable objects require. This render state includes the shaders and some extra information like the primitive topology and if it's an index trochel or not. Because particles, for example, are non-indexed trochels. And here we can see like an example. We have the edge buffer pass and we have two buckets. In the first bucket we have a single BSO that is for alpha tested objects, and for example trees and grass will be used at a specific BSO. Then we have another bucket that is for solid objects. Let's jump into the main course now. GPU occlusion performs all visibility tests and it will try to cull objects outside the first room, those that have zero screen area, those that have almost zero screen area and they don't touch sampling points, and finally occlusion culling using a hierarchical Z buffer. First room tests are using the bounding sphere. Maybe you remember from previously that we were storing the sphere in the renderable bounding volume structure. Because testing the first room planes is faster against a sphere. And the rest of the tests are actually using the AABB. Zero screen area and sampling point tests are quite useful in shadow passes, and this is due to undersampling. The whole process is split into two passes, and let's see them. This is the first pass. At the top we have the renderable bounding volumes of the, for example, Z buffer pass. The different colors of the bounding volumes show the render state buckets the renderable belongs to. This is 4 buckets. Basically this is the input of our first stage. And the pass will actually perform all tests for each of these bounding volumes. It will also do an LOD calculation, and then it will store an index of the surviving bounding volumes to a buffer here. Notice that the visibles are stored in a random order, and this is subject to atomic randomness because we reserve the position in that buffer by incrementing an atomic. This pass will also prepare the index argument, the indirect arguments, for the second pass. These are the indirect arguments, and it will also calculate a prefix sum buffer, which is one for render state bucket, and it actually points to the place where the second stage will try to place those renderables. We'll see later. And this is the second stage. It iterates the indices produced in the first stage here. And it will write a payload. This is it. And yeah, if you notice, the payloads are now ordered per render state bucket. This payload is 16 byte, and we'll see later a bit what it actually contains, things like transforms, uniforms, and geometry data. A final thing that it does is it populates the indirect arguments for its render state bucket, and also it uses the multi-draw, it updates the counts of the multi-draw trochels. The whole thing, it doesn't necessarily need to be in 2 stages. It can be done in 1 stage, but memory management is complex if we do it in 1 stage because of the different it's very difficult from the CPU to predict how much memory it will need for every render state bucket. And for that reason, it's divided into two parts, two stages. After the gbuff has run, we generate the hierarchical gbuffer, and that we will be using next train. For this generation, we use AMD's single pass downsampler. HB culling is pretty standard and well documented. In our case, we try to see if there is a possibility to use a more detailed MIP, so we can do more fine-grained testing. And this is the code snippet that does that. Shadows are a little bit different from the mains view visibility testing. Let's start with spotlights, which perform all tests, just like the primary view, except the hierarchical gbuffer test. Point lights are a little bit different though. The only test is a distance-based one, so testing the sphere of the light against the sphere of the renderable objects. This is another case where the sphere comes into the picture. And this is based on the assumption that the point lights only have a few meters of influence, so they don't need to have a more sophisticated occlusion culling scheme. The directional lights, sun basically, are a bit more complicated. We borrow the main idea from Haar and Aaltonen, which is in broad strokes takes its buffer's depth and it computes the max depth per 64 by 64 tile. One note here is that AnKi's depth is 0 near the near plane and 1 in the far. With that max depth per tile, it draws some boxes into its cascades HCB buffer, and then we downscale the HCB using again AMD's SVD as before. This is an illustration of the max depth per 64 by 64 tile, and this is used to draw these stretch boxes using the max depth tiles, and it's also using the cascade limits to limit the area of influence. This is the first cascade, second and third. And by looking at these HCBs, we can notice a lot of wasted space, because in the black part we don't actually need to draw anything. Can we do something better? Yeah, it seems we can. So the CPU will compute a conservative frustum per cascade as before, and after the max tile depth pass, the GPU will compute a new tighter bounds for each cascade and produce a new projection and view matrices. Then it will draw these stretch boxes with a new updated view projection, which practically, as you see here, it's actually zooms into the cascade. So in this picture we have less wasted space. Unfortunately, there are issues because this fitting changes changes on camera movement, which causes abrupt quality changes. One possible solution is to limit the amount of zooming, just to avoid this rapid change in quality. On top of the renderables, the GPU culling also culls every other CPU scene related object, and that includes lights, decals, fog density volumes, etc. When it comes to lights in particular, the lights just pass the same tests as the main views GPU occlusion culling. But this actually creates a practical problem. How the CPU will know which are the visible lights in order to write the commands that it needs to draw their shadows. The solution is to feedback occlusion results back to the CPU. So the GPU occlusion will write the visible shadow clusters to CPU visible buffer. The CPU will know about these shadow clusters a few frames down the line, which is not ideal because it means a delay. But unfortunately, there is nothing we can do at this point because shadows are rendered into an atlas, and changing the viewport directly is not possible at the moment. And clip lanes is not something that's supported in the platforms that we care. So unfortunately, we have to have this feedback loop. Once the CPU is aware of the visible lights that cast shadows, it performs rendering similar to the primary view. We have this two-stage visibility testing and the indirect drawing as before. But there is an optimization though. Stage 1 completes a hash and a flag. This flag is set if the renderables that are viewed by the light contain deformables like a skin or a particle emitter or something similar. The hash, on the other hand, is updated by taking into account the transforms of all the visible renderable objects by that light. Then the hash and the flag are passed into another compute dispatch that does vetting. If, for example, the light has objects that have moved, then it will render it as is. But on the other hand, if the light has objects that haven't moved or it doesn't contain deformables, then that compute job will go and nullify the indirect calls of the shadow passes and will effectively skip the shadow passes. In other words, if the surrounding area of the light hasn't changed, we skip the shadow rendering. This is a code snippet that shows how we compute the hash and how we set the deformable flag. Here we use the transform of the visible renderable. We transform some random point, doesn't matter. Then we use some simple hashing here that includes of course, the renderable unique identifier ID. We update the global hash of the specific light, and this is how we set the flag. At this point is looking at if it's a particle emitter, this is renderable, and if it's a skin. Another problem that needs solving is handling out-of-memory conditions. During visibility, the GPU allocates memory for the intermediate and final results. And when we say allocates memory, we mean just incrementing an atomic that points to some results buffer. This result buffer can't actually be the maximum possible size because the scene is very dense, might be very dense, and we cannot allocate the maximum because it can be extremely large. So what we do instead is that the CPU will have to pick a sensible max instead. So it says, for example, that the maximum allowed memory that will be used for visibility results can be like 1 megabyte. So there is a chance that the CPU gets wrong and this 1 megabyte is not enough and the GPU allocations fail. In that case, the GPU will have to gracefully handle this out-of-memory condition. It shouldn't try to write out of bounds, of course, and not fail the whole visibility testing, but it should stop processing more visible objects and somehow inform the CPU. Informing the CPU is performed by writing to some readback buffer. The CPU will read this buffer a few frames down the line, and it will do something about this out-of-memory condition. It may increase the size of the result buffers or the next frame, or limit the far plane, or throw a message to the user or something. So yeah, handling out of memory is a useful tool in general. Drawing is using KHR draw indirect count extension in Vulkan, which is called multi-draw indirect in OpenGL. This extension is a subset of DX12's extended indirect. So there is a single vk-cmd draw xxx indirect count call per render state bucket. We're not using the GL draw ID because that's a Vulkan only concept. So in order to differentiate between the draw calls, we actually use a vertex buffer. This vertex buffer is instance rate, and every instance gets a unique payload, the unique payload that we mentioned before. The payload has all the information draw call requires, and this is a pointer to uniforms, transforms, and to the mesh LOD if it's not a particle emitter. Now, an interesting question that arises is which packets we should draw first, because we have this ability now. So what we do in this case is that we draw the least expensive PSOs first, and the PSOs that have discard, meaning they are alpha tested, will always go last. This is based on the assumption that the majority of the objects will use inexpensive PSOs, so we want to draw them those first to occlude the depth buffer and prepare it for the most expensive PSOs that will follow. To understand how expensive a PSO is, we just look at the SPIR-V and count some interesting instructions. And to also understand if it's using a discard, we also look at SPIR-V and check if it has a op-kill operation. And here you can see the drawing part in action, one draw call per PSO. This is a pseudocode of the Vertex shader. This is the per instance payload that I mentioned, it's just for uints. The payload is used to access the transforms, the uniforms are passed to the pixel shader, and the mesh LOD is loaded here as well. Then the mesh LOD is used to access the vertices from the typed buffers that point to the UGB. And you can also spot the position unpacking here, the reverse of the quantization. Right, so next stop is extending GPU occlusion for meshlets. What we will cover here is how do we divide meshes into meshlets, and how we extended our GPU occlusion, and finally how we actually draw these meshlets. The first stop is in assets creation. When baking assets, we are using Mesh Optimizer to perform this meshletization. This is a new word. In our case, we decimate the meshes to produce the LODs, and then perform meshletization for each LOD separately. So there are no hierarchies like Nanite at the moment. Meshlets contain up to 126 primitives and up to 128 vertices. These limits are configurable, but they require a rebaking of the assets. Haven't experimented to find the optimal meshlet size for all architectures yet, but this works fine for some of the scenes I've tested. Meshletization produces an ABB per meshlet, an 8-bit local index buffer per meshlet, and also the vertex buffers, again, unique for the meshlet. It also computes a traditional index buffer for the whole LOD, And this is required for ray tracing because we want to be able to switch and because we want to use the same geometry for ray tracing. And another reason is that we also generate this global index buffer because we want to play with Meshlet rendering on and off. Yeah, basically we want to have the option to run them both and compare them. Unfortunately, meshletization creates a lot of duplicate vertices in some cases, but that's probably okay performance-wise. GPU occlusion builds on top of the previous concept and adds additional stages. Here we're adding Meshlet culling that includes backface culling, which is at the moment disabled because in the scenes we've tested it doesn't help too much. We are also checking if a Meshlet is out of screen and if it's touching the sampling points, and finally hierarchical Z-buffer testing. The result of the culling is similar as before, 16 bytes per visible Meshlet that packs the offset to transforms, the Meshlet primitive count, offset to uniforms, and offset to the Meshlet. This is the payload. Unlike per object culling, this time we need the two-phase culling. This is the first stage. Occlusion happens in, let's say, 3 stages. In the first stage, we perform parenterable testing, just like in part 2. And we also do the LOD calculation. The output is an 8 bytes per visible Meshlet. So this is different from the part 2. And these 8 bytes contain an index to the renderable, the bucket index, and the LOD and the Meshlet index. Additionally, we prepare the indirect arguments, just like before, for the next pass. And we create a perfect sum, but this time it points to Meshlets. The second path, it iterates this 8-byte output produced in the first stage. It performs the per Meshlet occlusion culling test, as we mentioned before. And if the Meshlet survives culling, we create a 16-byte payload, which is this instance rate Vertex. This payload contains, as we mentioned, transforms, pointers to transforms, uniforms, and the geometry data. We also populate another Meshlet buffer, this one, and this one contains the Meshlets that passed all culling, but they failed the hierarchical Z-buffer test. Finally, we update the indirect arguments of draw calls, and we'll see later what exactly these draw calls are. And now we are rendering using the visible Meshlets. These ones, we'll see later how we use those. Right, we render, and after that we generate a hierarchical Z-buffer, and then we arrive into the third stage. This is similar to the second stage. It does all the same tests as before, but this time it does them for the Meshlets that survived all culling except HZB. This time we use the updated HZB we generated in the previous slide, and the output is the same format as the stage 2. And then we render again the extra Meshlets and generate HZB again. And this HZB will be used in the next frame. So unlike when it comes to drawing, unlike part 2 that was using MDI, we're now using a single non-indexed draw call per render state bucket. The vertex count of this trocal is the number of vertices per meshlet, and the instance count is the number of visible meshlets of that bucket. The output payload from the GPU, the output payloads from the GPU visibility are fed into these trocals as instance rate buffers. So each meshlet picks one. If the meshlet has less than 126 primitives, the vertex shader creates degenerate primitives by setting the SV position to none. And the vertex shader is using the SV vertex ID to read the 8-bit local index buffer and index inside the meshlet vertex buffers. And this is a code snippet on how we access the local index buffer to load the vertex. Now let's go one step further and see how we use mesh shaders and how mesh shaders come into play. The meshlet rendering in using the non-index trocals that we mentioned previously is actually the fallback of the mesh shading rendering path. Mesh shaders were designed and implemented first, and the fallback path later. So everything we described before was built with mesh shaders in mind. The local index buffer, the meshlets, the size of the meshlets that is also derived from optimal mesh shader implementations. So everything that we mentioned before screams mesh shaders. GPU occlusion culling for the mesh shaders path is almost identical to the fallback path. We have per object occlusion culling, then per meshlet culling. We render the visible meshlets, HB generation, second phase of culling, render again, and HB generation again. Our mesh shaders are not paired with an amplification shaders in this version. Previous attempts had amplification shaders. We have more details later, but due to maintenance cost, there was a decision to drop them and have the fallback path and the mesh shaders path to be compatible as possible. Drawing is now performed with an indirect dispatch mesh, the render state bucket. Internally mesh shaders to additional culling tests that are per primitive. These tests are backface culling and coverage testing. But yeah, nothing really special about it. And now we arrive in the final chapter, which is some numbers. But first, let's show the two scenes that we used for benchmarking. The first is an abstract programmer's art scene with 10K objects and around 36 million triangles in total. The objects are very simple, they have very simple geometry, but there are many of them. And yes, it looks like a level taken from an earlier Serious Sam game. Yeah, I'm a big fan of those games. The second screen has less programmer's art. It has more detailed meshes, but fewer of them. So it's like 1.5K objects and 2.7 million triangles in total. Here we have some numbers that we compare the three modes the engine supports on an NVIDIA 4080. On the left, we have meshlet. Sorry, on the left side here, we have we're drawing the full meshes using MDI. In the middle is the software meshlet rendering fallback path, and on the right the mesh shaders. And as we can see, the mesh shaders are a clear win in the Joggle scene. In the Pali scene, things are a little bit murkier. Mesh shaders come on top, but only because they help in the shadow passes. For the G-buffer pass, it seems MDI is the winner, so drawing the whole object. And here we have the full frame in Insight. Here we can see the first and second pass of the GPU occlusion, which are quite small if we compare them to the whole frame. Here we have the G-buffer pass. Here we have the drawing of boxes for the shadow cascades. Yeah, unfortunately this seems quite a bit expensive and something that we need to optimize. And here are the shadow passes for the for cascades. This is in the Drogolcy. Now let us look at amplification performance. In our first attempt, the mesh shaders path were performing cluster culling in the amplification shader. In a later version, as we mentioned before, we moved the cluster culling to compute to decrease the maintenance cost. But it turns out that the amplification part was slower, and after multiple attempts to optimize it, it still remained slower. Yeah, this is on NVIDIA, and we also have recently a few more numbers on AMD that the amplification shaders are not as performant as we expect them to be. And this is the end. We arrived at the end. Hopefully you found this useful. And if there are any comments or questions, leave them in the box below. Thank you.